Welcome everyone to the IDRiM Podcast. Finally, we have another podcast again after some breaks we have after the IDRiM conference, and particularly this one episode is intriguing and exciting as we delve into the series of the current flood disaster that occurring in Indonesia. And in this first of the series, we explore a groundbreaking new study published in Nature Communication, Earth and Environment that directly links forest loss to increased large-scale flood risk using over 50 years of real-world hydrological data. As we know, flood risk is rising globally, and at the time, forests are disappearing at an unprecedented rate due to the forest deforestation and extreme wildfires. Today, we discuss publications by Professor Ashish Sharma and his teams that directly connects these two trends in a way that could reshape flood research science. To get us through this important research, we are joined uh, by him from the University of New South Wales in Australia. And welcome to the podcast, Professor Sharma.
Hi, Harris. Thanks for having me on.
Mm. Okay, so first of all, can you explain to us that your motivations, what originally motivated you to investigate this research, the relationship between the forest loss and large-scale flooding? Was there any particular event, debate, or gap in the literature that pushed you towards this research?
So we have been investigating the impact of climate change on flooding for quite some time, and we have some very prominent papers that have shown that the moderate floods are actually going to decrease in the future, while extreme floods will increase in the future. But we had not really looked at this critical problem about forest loss before. So during a PhD project, this was by Tai-Ho Kang, a very gifted PhD student who's now Dr. Tai-Ho Kang and works in K-Water in Korea. We basically realized that we have an opportunity. And the opportunity basically, showed to us during an unfortunate time where we were having widespread forest fires in Australia. So essentially, the realization that we are having forest fires also led us to realize that we have data for these forest fire impacted catchments. And these forest fire impacted catchments are essentially a surrogate to catchments that undergo deforestation. And this deforestation is something that has always caused confusion in the public discourse. People have been, complaining that if you take the forest down, there will be an increase in floods. But nobody has been able to pin that thing down. Nobody has been able to prove it because it's just a very difficult problem to work on. So we use this forest fire as a surrogate of deforestation to try to understand how exactly forest loss might impact flooding in course of time.
Yeah, so what did the results show, first of all? Because personally, from my experience, I would have thought that reduced forest cover meant that you get more runoff, therefore leading to more floods. But what did your results actually show you?
They showed exactly what you said. The reduced forest cover increases the peak flow very significantly. And very significantly means that if, say, you have 64 catchments in a region, this is a very crude analogy, but I hope it gets the point across. So under normal conditions, you might have one in those 64 catchments exhibit flooding. But after a forest fire, you will have as many as 8 of those 64 exhibit flood conditions. So basically, the loss of the forest cover is changing your risks roughly 8-fold in terms of forest loss. And this is the type of forest loss associated with a forest fire. So which is quite different to the types that we are finding right now in Indonesia and Sri Lanka and other places, where it also leads to landslides, to mudslides, to all sorts of other catastrophe that actually increases the impact, the death and devastation downstream many, many fold.
What I'm just thinking is, though, and I'm going to throw a caveat in here, is that there was some discussion I heard years ago that forest fires can what we call like bake the ground, so it means that it makes it harder for water to permeate. Is that such a case in these scenarios, or is it been so long that this situation might not be an issue in the study?
I think that is actually true. Forest fires can create to a certain different surface condition that can, in theory, increase the magnitude of the flood. And this is something that we checked very carefully. So basically, because we have data for so many catchments across so many years, we could devise our experiments to quantify what was the main cause of the flood increase. And while this particular change on the surface properties is important, the loss of vegetation by far was way more significant. And that was basically the main dominant factor that led to that 8-fold increase in risk of flooding.
Let's return back to your paper after the discussion of the preliminary results. That in your paper, basically, your analysis spans more than 50 years, and it's basically you're doing that in the Southeast Australia. Why is the long time horizon is important for detecting change in extreme flood, and why it's good thing that you have in Australia?
Yeah, that's a very important point. So any statistical change requires two things. It requires, first of all, lots of data, and secondly, it requires stationary conditions. That means that you have basically a system where there is no systematic change, such as urbanization or climate change. Now, as far as climate change is concerned, that is something that is happening continuously behind us, and that is in the background. So basically, we can't really escape the impact of climate change, but the impact of climate change is probably not as significant over a 50-year time period as it will be over the next 100 years. So let's ignore climate change for now. Having the same type of conditions requires catchments that are not undergoing urbanization. And this is something that we are very lucky to have. The Australian Bureau of Meteorology has over 650 catchments that it has meticulously collected streamflow data for a very long time. And these catchments are certified as being anthropogenically unaffected. Means there is no significant impact of urbanization. There is no significant farming in these catchments. They basically represent pretty natural conditions. And in our case, we have basically taken a subset of these catchments that were fire impacted. So we had essentially the opportunity to compare how these catchments were preceding a fire and how they were basically following the fire events. But that doesn't completely explain our statistical experiment. The second thing that causes changes in floods, especially in Australia, is this thing called the El Nino Southern Oscillation. So the El Nino Southern Oscillation is the biggest driver of variability in rainfall pretty much across the world. In fact, there was a paper that we had written many, many years ago that said that if you had to identify one single factor that is changing the global climate significantly, it is essentially the El Nino Southern Oscillation, and it has global impact. So in Australia, you can't really consider conditions associated with the El Nino phase, which results in a drought, and the La Nina phase that results in a flood. Now, what happened over here is when we considered the forest fire years, they essentially did not correspond to these El Nino or La Nina years. So what we had to do was to separate the years out where similar climatic conditions were prevalent. And that allowed us to compare the impact of the flooding associated with the fires with the impact associated with non-fire events under same climatic conditions.
So, just in you were talking about the El Nino in your study. How frustrating was it during that few-year period where there was that, about a 10-year drought in Australia? How frustrating was it in the data where you could just see this bit where there's no real data you can see in terms of flooding?
That is a completely outlier period of record, and that was actually quite frustrating because our analysis for the forest fires reported over here cannot use this later part of the data because we have so much more data associated with forest fires now. But the point is that those forest fires were associated with the El Nino conditions, the later length of record. The earlier record that we have considered over here was basically considering climatic conditions that were non-ENSO impacted. So, I mean, the problem was that we wish that we could have more data because any statistical hypothesis test, the data is the most critical part of that whole journey. And by deleting that extra amount of data, basically made our conclusions, let's say, less strong.
Yeah, well, that's discussion of the ENSO and La Nina you also bring up here in the just now the state hypothetical test. Can you explain what this method is in the simple terms, and in your case, why is it powerful for the causal inference of these cases that you're investigating?
Sure. So normally when you estimate a probability, so in the flood case, it is called the probability of exceedance. You look at something called the annual maximum flood, and you take a certain threshold and you count how many years is the annual maximum flood greater than that threshold, and you divide it by the total number of years on record to estimate the risk or the probability of exceedance. Now here we have a slightly different situation. We have a number of catchments. So essentially, each catchment has its own flood magnitude because its area is different. Smaller catchment will have a smaller flood, a larger catchment will have a larger flood. So we need to basically find a different way of quantifying the change in risk. So what we did was we basically identified the rank of the flood on record for each and every catchment. So suppose we have 50 years of data, each and every catchment will have essentially 50 annual maximum flood values, and we can rank this data accordingly from 1 to 50. And based on this 1 to 50 ranking, we then pooled together the catchments that corresponded to just the forest fire years, and then the non-forest fire years that were independent, that coincided with the same climatic state as the forest fire years. And so basically this gives us something, a statistical method that allows us to compare specifically the change in risk associated with the forest fires with the normal conditions.
Yeah, so when I just now want to move into a little bit into the methodology of the study. And you applied what you called state-controlled hypothesis tests.
Yes.
Could you explain what that means in a simple terms and why it can be so powerful for causal interference?
Sure. So the state over here is the climatic state. So what we are doing over here is we are firstly identifying that floods are dominantly a function of the climate. We have taken the floods during the fire years. We have identified what is the prevalent climatic state associated with those years. And then in the remaining historical record, before the fires actually occurred, so you're having a forested catchment in that situation, we have identified which years had the same climatic states. So now basically you have a bunch of catchments where you have the fire impact in certain years, and you have the same catchments under the same climatic conditions under that you have that allows you to estimate what would be the flooding if you had a full forest. And this is basically the state controlled climatic test hypothesis test that we are using over here.
Now, a part of the methodology that you mentioned, so you also use some data on the satellite, and particularly in the satellite-derived leaf area index to quantify the forest loss. Can you explain more about this data and how reliable is this metrics, and what it enables you to do the research that perhaps wasn't possible before?
So as I said, we are having 50 years of data, multiple catchments, and we have essentially taken data for the fire years, and the fires were only in a handful of years. And then we have identified similar years, climatologically similar, and we have compared the fire year floods with the non-fire year floods under the same climatic states. Now, this gives you a big change in risk, but you still have questions. You still have questions because this is just one line of evidence that we are pursuing. If our hypothesis is that the forest loss is likely increasing the floods, would it be possible to just compare data on the flooding in catchments that were not impacted by fire in the fire years? So fires did not cover all of the catchments in that region. So essentially what we did also do, in addition to comparing across time, we compared across space. So in the fire years, we compared the floods associated with the fire impacted catchments with the floods associated with non-fire impacted catchments. And that was the second line of evidence. Now, when we talk about non-fire impacted catchments, you have to quantify the magnitude of forest cover that you have available. And to do this, we use something called the leaf area index. So the leaf area index is a very well established measure of canopy as seen from the sky. So if you shine a torch down from into the canopy, you are essentially able to see how much of the light filters through. And that is what is used as a basis of measuring the leaf area index. Now, we could compare the leaf area index that was there in the fire impacted catchments and the leaf area index that was in non-fire impacted catchments to ensure that we were having two very different conditions. And that allowed us to basically pursue the second line of evidence that showed quite clearly that if the leaf area index was higher, the flood that we were getting was of a different magnitude compared to the fire impacted catchments that had a low leaf area index.
Okay. That was a very good and extensive explanation of the method. Now, given that you explained several evidences that you found and methodology that you used, can you explain more on what was the key and important quantitative results in this paper in terms of the change in flood frequency and magnitude, as you mentioned, after forest on the canopy loss? How dramatic was the increase in annual maximum flood events?
Yes, so because we were able to develop a probability model that allowed us to essentially quantify the risk of flooding during fire impacted years and compare that with the risk of flooding during non-fire impacted years, we could see that the probability of flooding is undergoing a 8-fold increase when you have forest cover. So essentially, when you lose forest cover, then there is an 8-fold increase in flood risk. When you have the forest cover, then the floods are of a remarkably different magnitude. And I think that the next thing that is actually quite impactful is we have a conceptual diagram in the paper that talks about why exactly is this change in risk occurring. And the main culprit is two things. It is the amount of water that the canopy itself stores, that is called interception. And that is when the rain falls, when you and I need to escape from the rain, what do? We go stand under a tree because it's only after many, many minutes of downpour will the trees basically start raining through. The rain will start dripping down. The tree holds a lot of the rain. And you might think it is not important, but actually that matters a lot because what it does is it delays the accumulation of water on the ground and its transfer to the river and finally the big river flow. So your big flood is essentially staggered over much longer times because of this interception. The second factor that happens is all the leaf litter, the leaves that fall down to the ground. They also have a way of increasing what we call the roughness of the surface. So basically, because you're having these clumps of leaf and branches and whatnot on the bottom of the tree, the water flow gets impeded. So you sort of have you can say you're kind of slowing the pace at which water will flow towards the river. Cumulatively, this all reduces the peak flow. It increases the timing of the flood event and it reduces the peak flow. So it does not do anything in terms of flood warnings, but you are having very clear differences in terms of the peak flood. The volume is still the same, probably, that finally will be flowing through, but it won't be coming at one instant. The fact that it comes at one instant is what causes all the death and devastation. If you can stagger that flood out over time, it's a lot simpler situation to manage.
Yeah, so what I want to do now is take, your results and just discuss them for a bit more modern context in Australia. So anyone who's listening to this is not quite so certain, Australia's been through probably both ends of the spectrum in recent years with their climate conditions, and particularly in Eastern Australia. So we had the wildfires late 2019, early 2020, some of the worst Australia's ever seen. And in recent years, and I don't know, this is a perceptual thing from being in the UK, of someone who is interested a lot in Australia. Australia in 22 to this year has had a lot more flooding. In particular, around North Queensland, in Cairns, and in New South Wales itself. Is the loss of the forest cover from 2020 impacting, this increase in floods we've seen in the last few years? Or is there more external factors like the El Nino, like climate change, like urbanization causing these increases?
I think it is more to do with climate variability. And to some extent, climate change that is increasing the flooding in Australia. And Australia is a very, unique setting because here the government systems are very carefully developed and very carefully implemented. So you cannot have rampant deforestation without consideration for how the forest regrowth will be occurring. I mean, deforestation is there everywhere in the world, but it's about sensitively managing the whole deforestation process. So I think Australian flooding is less impacted by deforestation per se, as compared to essentially changes in the climate, especially antecedent moisture conditions or soil wetness. If you have periods of rain, it really, makes the soil very, very saturated. And any new rain that falls in after that leads to a magnified flood. And basically, that is what we have been seeing in Australia, because once we flipped from the drought to the flood, then you're just having flood after flood after flood. And it's partly to do with the soils being a little bit more moist than they are under normal conditions. Now, the same thing was exactly the case that was leading to drought after drought after drought, because basically the soils did not have any antecedent moisture. See, even if you had a little bit of rain, that entire rain was just soaked up in the soil. It was not leading to any flow, any revitalization of the environment. And so basically it was creating a much more compounded situation for both drought and floods, for both forest fires, as well as the situation that we are having now. But Australia is unique. The situation is not faced elsewhere in the world. So, I mean, the first story about deforestation causing flooding actually dates back to the French Revolution. And this is something that we came across in the literature, that people have been saying anecdotally after the French Revolution that, hey, it is the loss of the trees that is increasing flooding. Then you're having, again and again stories, instances of deforestation in South America being anecdotally associated with big flood occurrences. The same thing probably is something that I am told of is happening in India, especially in the northern part of India, very regularly, where they are having, tree clearing or basically changing the native tree habitat to new tree types. And you're having all of these crazy mudslide events, landslides in the mountains, which are basically getting barer and barer. Because what happens is once you do remove the trees, then the root systems that kind of anchor the soils together, they are no longer there. So you have this big destabilization event in the case of very saturated soil coupled to very high downpours. It just triggers off a mudslide or a big avalanche. And this is something that can be fixed to quite an extent, not to 100% extent. But if you do sensible land management across the world, if you have policies and plans in place as to what you need to do when you do have to take a tree down, these things can be contained to quite an extent. And I hope it will be in the future.
Okay, so actually, what you've done is actually touched on something that is actually really quite important right now, in particular in Indonesia. Now, by chance, my co-host is actually Indonesian as well, so actually I'll bring him in on this as well as yourself. So what we're seeing, so we're recording this just early December 2025, and there has been a substantial flooding event in Sumatra. Now, that is partly, of course, due to a cyclone. But Harris, Sumatra. Yes. Now, from an external point of view, I always think Sumatra is, very forestry.
Yeah.
Has there been an undergone of the forest cover, in particular in Sumatra in recent years, especially with deforestation and development?
Well, as we talked earlier, but basically, and the points that Professor Sharma here explained with examples with India's and different countries earlier, Sumatra has been undergoing deforestations since 15, 20 years ago, where the increasing needs or sponsorship from the government to use the more palm oil changed the entire landscape of the forest variations there. Many of them now try, basically at the time they sponsored big companies, but now also the locals try to change the originals, the forest with the palm oil, which now make I'm not sure whether to explain it correctly because I'm not expert on that, but it's soaking a lot of water, the palm oil from the soils, and as I mentioned, it doesn't cover any water when it rains down, and it's actually now it's the biggest floods that they experience it. That's affecting more than 3 provinces at once. But the floods like this actually has been occurring several years ago, even around 5 and 4 years ago. But it's like goes under the radar because like at the time, the COVID played a part of shifting the narrative, and as well as the several big disasters actually occurring there, such as a tsunami and an earthquake, that people more focus on that disaster instead of the flood. That okay, this flood is like coming on several days and then just dissipated, and perhaps not as big as now. So that's many people think that play a very big part of what's happening right now. And as I mentioned as well, it has a lot of landslide there where we saw in the videos that it's moving houses because like since the forest is changed with and the roots that actually anchoring as a Professor Sharma briefly explained is actually moving all the soils all together because no anchor at all right now. And then as the climatic effects coming down since the middle of November, so the cyclone came, and then it makes the matter worse. Not only like the increasing the intensity of the rainfalls, but also the conditions that actually make it prominent for floods to make these big disasters. Now, go back to you, Professor Sharma, that you mentioned that the striking thing is like the flood will increase at times, and like this kind of thing is actually already occurring in the world even since French revolutions and many part of the world, and probably will go worse and worse in the futures. Is there any ways for us to prevent this? Basically, after we we got the deforestation now, and like that's the fact that we need to accept that. Okay, then if we can actually predict whether the cyclones or the El Nino will come, what kind of preparation that we can make from your side that we can think, okay, we know the data that there is deforestation in this area, and we know that we can predict the next climate events, and what can we do if we have this in order to reduce the flood risk?
Yeah, before I answer that, let me
Yes.
just add to the point that you
Yes.
made, Harris. I mean, that is a very good
Yes.
point. Well, like the situation in Indonesia, you know, that basically highlights why it has been so difficult to quantify the impact of forest loss on flooding, because basically everything is changing. You have a cyclone now. So to really compare the situation, you need to have the cyclones of the same intensity under, forest-free environments and forested environments. And this is the reason why this debate has been going on since the French Revolution, because at no time did you have large expanses that were essentially deforested and not deforested, undergoing the impact of the same climate for you to be able to compare. All such studies that had happened in the past were over simple little paired watersheds, experimental watersheds, a few square kilometers that you could really keep all the data together and actually make some claims. But you could never really say this across big regions, big tracts of land. And I think that is probably why nothing really has been done in terms of the enhancement of flood risk that deforestation really causes. Because to do something, you need to have data, and there was never any data. So I think by using the fires, I mean, the fires cause a lot of tragedy and devastation. But basically, this was one positive thing from the whole thing, that we can use the fires as a surrogate to deforestation and actually pin down the change in risk associated with floods. And that is a big one. Now, just coming to what you said about what we can do in the future. Look, floods happen dominantly because of the climate. And that is something we have always known. But the same climate can create a markedly bigger flood if you do not have forest cover. That is what our study has shown. So basically, you can't control the climate beyond the limit. So we are stuck with whatever surprises the climate will throw to us in the future, which will get even more and more unpredictable and variable as the world warms up. I mean, remember, the big kink in that climate change curve starts after 2030. So once that happens, then you will start seeing a big ramp up of the impacts of climate change across the world. But what we can do is we can actually control things on land, on what grows on land, what type of barriers we have for flooding. I mean, this is what we have done to our beautiful cities across the world. We have, to an extent, made them flood-proof by putting or engineering some mechanisms that keep the floods at bay or control the floods from crossing certain thresholds. One of the biggest wonders of the world is the Netherlands. I mean, half of the country is under sea level. So essentially, they are not having the impact that you would normally have in any other coastal zone because they have engineered a solution. Well, deforestation is a way of changing the landscape, but maybe what we can think about doing is to do controlled deforestation or selective deforestation. Maybe what we can do is when we do let's say property allocations, or we do planning as to who gets to live where, we keep this in mind. What is the impact of land use change upstream of them that might change their flood characteristics? And all of this is actually factored in well in advance before people are able to live. So basically, if you're doing deforestation, make sure that the increase in flood risk will not have a direct impact to populations living downstream. And this is not that hard to do because you're not clearing the entire forest in one go. You can selectively clear bits and essentially regrow bits in a controlled way so as to keep things under control. And unfortunately, that is what we have not seen too much of, especially in developing countries across the world, because it just seems too easy to make money by cutting a tree down. And that is something that we need to learn from and try not to repeat in the future.
So my next question is, and it's kind of two questions linked into one here. Have Australian cities then really prepared? Because what we've seen in recent years is with Townsville, with Cairns, being, severely flooded in recent years. But also, are we expecting with, this deforestation, more peak floods or more frequent floods, or a combination of both, that these cities are going to have to prepare for?
So that's an interesting question. So, I mean, the situation in Townsville or in other parts of Australia is a bit more complex because, these are historically developed, let's say, settlements that are in certain geographic locations which have a tendency for higher than average flooding. So the tree loss is something that I believe is not the dominant factor for the increase in flooding that you find in Australia. I mean, it has an impact. I should not say that it has no impact. It has an impact. But basically, it does not have as much of an impact as you're seeing in Indonesia or in Sri Lanka. The main impact of flooding in Australia is really the climate. It is such a variable climate. I mean, the El Nino Southern Oscillation probably has the most significant impact in terms of variability in Australia. So you have this massive land that is so dry, but then you have these big anomalies when you have big rains, and that creates, unexpected flooding. You said something about moderate floods and extreme floods. That's a very important point, actually, because extreme floods are the life-threatening floods, and they happen as they do, and they are likely to increase with our atmosphere holding more and more moisture as the climate warms up. The moderate floods are a different category of floods. The moderate floods are the floods that keep our reservoirs full, that allow us to have water in our taps, that ensure we have water supply reliability. Now, how do these moderate floods occur? These moderate floods occur by basically either extreme rains falling on dry soils or moderate rains falling on wet soils. So what is happening is, because soils are getting drier and drier as the climate warms up, these moderate floods are actually decreasing everywhere in the world. And this is a big concern, because what it does is it directly reduces the reliability of water supply. So look, Indonesia does not have to think so much about the reliability of water supply, but when you look at Australia, it's a dry country. So almost all cities have their big water supply reservoirs sitting upstream, and they are the ones that are ensuring that we can have cities of the size of 5 million people, as is the case in Sydney. This would not have been possible had we not had the dams, had we not had the reservoirs. Sydney, by nature, would not have been able to have more than, 50, 60,000 people. 5 million is simply because of engineering. Now, these reservoirs are filling because of the moderate floods. And we had another study. This was not the paper that we are talking about, but this was a study that came out in 2021 that actually projected that the reliability of water supply across the Australian continent will reduce by 30% by the year 2100. And the scary thing about it was that 30% was a reduction in the same direction across all of Australia. That means there was not one part of Australia where there was an increase in reliability. It was a consistent decrease in reliability across the entire country. Now, Australia is already water starved. Okay, so imagine a 30% drop in reliability. That is something that will create havoc in course of time for our water supply reliability, for agriculture, for all sorts of issues. So I'm deviating a little bit from the forest loss issue, but essentially highlighting that there are very huge challenges that are brought about simply because of climate change. And these challenges have impacts on the flooding side as well as the water supply, the drought side, and we cannot ignore that.
I mean, you put a more scarier thing here after the flood and drought and all. You mentioned that water supply in Australia was decreasing at 30%, and you keep mentioning that the wonders of engineering actually have been keep flood at base historically in many parts of different worlds. Now there are many supports, or I guess talk and assertions towards nature-based solutions. Of course, nature-based solution is very different from engineering. I mean, do you have any idea that which kind of nature-based solutions that can be implemented to face the bleak future that we seems to have due to the deforestations and floods, and perhaps you can also mention to face the reduction in water supply.
So, but by engineering, I mean anything that requires human intervention, anything where humans have decided something needs to happen. I put nature-based solutions within that category, because they are one tool that is available in our arsenal when it comes to flood protection. And it is a very benign tool. It's a very, solid tool that does not really have these big levees or dams or, other type of rigid concrete infrastructure. They are actually just re-enhancing the landscape. But re-enhancing the landscape is also controlled by us. Like we have decided that this is how you will, this type of a revegetation strategy is what you will adopt. It will have this particular type of vegetation. You will have this kind of water sources, wetlands that impede the flow of water. And this requires, again, very careful planning and strategizing. And it is definitely to be encouraged. But this does not simply mean letting nature, take its own course. It means essentially reshaping nature in a way that can meet multiple purposes, one of the purposes being flood mitigation. So I think we have to do everything, all types of tools that are available to us, all types of tools that will be accepted by the society, because after all, at the end of the day, the society needs to be on board. And the society is much more on board with the nature-based solutions because they don't just meet one objective, they meet multiple objectives, and they must be promoted, over course of time.
Yeah, and here in the UK, it's the same situation right now where hundreds of years of progress, not really progress, of taking the peatland away, has now been reversed because we realized the peatland was actually critical to stopping flooding. Well, going back to, what are the solutions, and, engineering type of approach, isn't the concern though, if we have a human influence on the nature-based solutions, that we're not really going to be helping the situation? So as you mentioned, Harris, about, putting palm, trees in, isn't there a potential that if we artificially encourage the regrowth and the reforestation, that we could do it all wrong and actually not really help, and maybe leaving nature to fix itself might be a slower solution, but a more efficient solution?
So look, that's a very true point. I mean, engineering is littered with disaster stories of how we thought well and we did something, and then over course of time we realized that hey, it's caused all this damage. But letting nature be itself or going back to nature also requires that we drop the population of Sydney from 5 million people to a handful of thousands. So it's a double take. One cannot think of a solution without considering the human implications. The fact that we have these concentrations, ghettos across the world, that will become basically more and more ghettos as technology evolves. I mean, it's not very long into the future that we have humanoid robots doing all of the farming for us, and essentially people are just going to be concentrated in cities, and they'll just go for holidays to the countryside. So I mean, this is fast forward 100 years. None of us will be around, but that is something that is quite likely to occur. So if you will have this type of a situation, then I think one has to have an open mind. What the solutions are, what our goals are. Our objectives should not be over a very short time frame. They need to be over short and medium term and long term time frames. We have to think about not just our generation. We have to think about the next generations as well. And this is something that basically our policymakers, our politicians need to get on board about, which is probably the biggest challenge when it comes to policy making across the world. They are just let's say they just react to 3-year or 5-year or not a lot longer objectives. But what really needs to be thought about is really long-term objectives along with the short-term ones. The short-term ones are important. They must not be disconsidered, but the long ones need to be also taken on board in devising policy.
Yeah, that's, I think, a very good point, but the most difficult one when we talk about the long-term solutions. Although in the recent years, it's become many countries adopted like that because okay, we have big change in 2100, 2050, and like how we can face that. But again, I guess in many developing countries, they haven't think about that. They haven't thought anything about that, and like it's always the events come first and how should we react of this instead of preparing for the future events. Now, from the interesting discussions that you provide suggestions and results, that striking results, can you perhaps have any limitations of this study that you have, and perhaps what is the main difficulties to transferring these results to other part of the world? As you mentioned, that Australia is unique, you have a rich of data, like that.
I think we took advantage of having very extensive data set of flooding on forest clearing because of forest fires. And that is a very unique situation in Australia that we dealt with. I guess the strongest part about our research is that we could finally link it to two very well-known and well-studied processes, which is interception and essentially the moisture that is stored by leaf litter, etc., on the ground. So what needs to happen next, if you cannot have data, just like we did, is to do the next best thing. And the next best thing is a model. If you have models in place of a catchment and you are able to simulate the flooding that occurs in that catchment through rainfall data that is now available literally across the world, measured by satellites. It has problems, but it's still a very good tool. I mean, I recommend this to my students to use satellite rainfall data and cross-check it with gauges or maybe scale it based on the gauges so as to get some realistic estimates in places where you don't have rainfall data. So if you have the climate, you can simulate what exactly is the flood going to be like under extreme climatic events and simulate it again by clearing the forests. So you should be able to quantify what exactly is the monetary loss, damage that will be caused by taking the forest down. If you're able to calculate that, that should be compared against the gain of clearing the forest. So you do a proper cost benefit analysis and then you figure out what is the damage, what is the gain, and you use this very carefully in any future clearing activities that are many places they're just done blindly. You just go ahead and do it and worry about the consequences later. But if you can actually do it now in advance, you can do a scenario assessment. And I'll take it one step further. I would love it if the risks that we are calculating, the increase in risk, 8-fold increase in risk, can actually be the basis of lawsuits by impacted communities. I mean, who commissioned this forest loss? Who is standing to benefit from this forest loss? If there is an 8-fold increase in risk, and this deforestation is actually causing damage and death and devastation, why should the impacted communities not be able to lobby and actually hold the people or the policymakers or the companies that are creating this damage to account? So we were talking about policy having a 5-year reach that most of our policymakers just think about 3 to 5 to 7 years and that's about it. The moment you bring the law into our hands, you put it in the hands of the people who are impacted, that will put the long-term objectives much more prominently in the minds of the policymakers. They would not think about a quick profit tomorrow. They'll have to think about the continuing losses that happen many, many years into the future. And they will have to basically justify to the populations, to the communities, to the people who put them in power that, hey, this is really worth the loss, in terms of the profits and the damages this is expected to cause.
Yeah, so now what I wanted to think of is what comes next. Now, what is this research going to do, in terms of where you're going to go next with it? But also, if you had unlimited data and funding, what would it look like? Because I know there can be two different things.
So, look, if we had much more data, we would have even greater confidence in our results. So suppose we had data from the French Revolution time until now. We wouldn't have to pool catchments across space. We could just do analyses over, individual catchments over time and see what exactly is the flood impact that we would be having. So more data is definitely very, very valuable. But having said so, I believe the analysis we have done is kind of enough, in the sense like this hypothesis had been lingering on in the scientific literature since many, many years. But nobody had been able to pin it down to a number that, hey, what is the increase in risk the deforestation specifically is causing? And we have shown an approach that allows you to actually quantify, what exactly is the change in risk. So using the same forest impacted catchments, other researchers, other groups can basically convert it to the change in risk for different levels of leaf area index change in the same catchments. And if this is available, then you can use this possibly as a means of generalizing what exactly would be the impact. But I think the biggest thing that can be done is this scenario modeling exercise that I mentioned before, that you use climate data, because climate data is now available literally everywhere. And we actually run scenarios of what the floods would have looked like had we not had deforestation in Indonesia or in Sri Lanka or any other parts of the world. And this is something that I would love to get motivated, clever students who, commit themselves towards finding an answer to this thing. And basically, this is a problem that is a burning problem. And I'm sure over the course of time, research would be able to give us a tool where this type of a scenario analysis can happen in a generic manner and basically gives policymakers something that gives them a number that, okay, this type of forest loss will have this much of an impact in terms of flooding.
I like how you touched upon, you're talking about your students there. So finally, as we're coming up to 1 hour already, for early career, researchers and students who are entering the disaster risk field or the hydrology field, what does this study say about where the field is actually going to be heading in the next 5, 10, 15 years?
Oh, that's a tricky question to answer. I have graduated 44 PhDs to completion. And, many of my students are in very highly respected academic positions, industry positions, and so on and so forth. I guess my philosophy of a PhD is to pick a problem where you appear to be coming to a roadblock, where there is no answer in sight. because I feel that, with clever people being put together in a team and a 3.5, 4 year time frame that a PhD normally takes, no problem is unanswerable. So I think that is probably what I would say to early career researchers. You know, I tell my students that I always have this OneNote file that's called Crazy Research Ideas. And I always tap into it whenever I have a new PhD student application. So basically, have your file of crazy research ideas and crazy research problems, even if you don't have an idea. The problem needs to be a genuine, a good one, because the world is changing. I mean, our resources are changing, our computing resources are changing, our data resources are changing. Satellites have made it possible for us to basically see things at very fine scales. I know with uncertainty, but still, all these things are happening very, very quickly. And this will just continue to explode in the future. But pick good problems, pick problems that really matter to society. I mean, at the end of the day, I did not become an academic to solve flood problems or drought problems for the richest people in the world. It is to the people who really are in locations where there is poor governance, where there is no data. Uh, that's the real problem that needs to be tackled and solved. Now, we just completed a project where we are trying to forecast sudden reservoir releases from one country into another country. Specifically, this is North Korea into South Korea. And the challenge that we faced with the wall that we had was that we knew nothing absolutely. Not the rainfall, not the stream flow, not how big the reservoir is, not what is its storage capacity. We knew nothing at all. And we had to come up with a system that could actually issue warnings that were usable by the community which were being killed because there were no warnings given. And I mean, the good thing is that we've managed to do it in course of a PhD project. So these are the type of problems that ECRs need to pick. Pick something that appears impossible and just put your heart and soul into it. And when you get stuck, reach out to others. It is not your problem alone. I mean, it's a community problem. And there is a world of scientific knowledge and expertise out there. And it just requires a little email to start a discussion going, and it's these discussions that basically lead to solutions in course of time.
Wow, that's very nice, very nice motivations for early career researchers, and basically a call for everyone is still looking for PhD to coming to Professor Sharma lab if you have any interest in hydrology and floods and anything that we discussed today. It's very inspiring and exciting discussions. Thank you again, Professor Sharma, to coming here again to talk your research to our podcast. And for everyone, we was, as I mentioned in the beginning, that this is part of the series that covering the current disaster in Indonesia. Now we discussed about how the deforestations actually can increase the flood to 8-folds, and we will discuss more about what happening there given the occurrence of cyclones and what happening in the fields. So stay tuned for us and see you next time.